hope everybody's doing okay. And make sure this is streaming properly. Looks like that's good. So I'll wait till a few people come in. If somebody joins today before I get started. As promised, I'll be doing some electromagnetism. Um, I was quite interested in the derivation. I knew there was a derivation of the speed of light from basic electromagnetism principles. And it just so happened that my professor in I'm a learning assistant, as many of you know, and the professor in my class that I L in, he actually did the derivation the other day. So I'll be going through the derivation as he showed it in class that day, and basically how we'll see how we can get light, the speed of light from basic principles. Uh, and I'll also start a bit by how I measured it physically, because the derivation, I guess, doesn't take too long, even though the math, um, depending on your familiarity with integrals and such, could be a bit complicated. And it was going on, Catherine. Awesome. It did go well, exactly. It went pretty well. I ended up getting a 80 something. I thought I had a 93, but one of the answers that I got right, technically I got the answer right. It was a concept answer, but we had to explain something about quantum mechanics, and he felt I didn't go into enough detail. Like I left off one little detail, which I thought was self-explanatory because I drew a diagram as well. So I drew a diagram, and I kind of like accepted the diagram as part of my explanation, but he kind of wanted me to say what the diagram was saying in words. But I don't really sweat it because I did. There was a few details I missed on a few later problems, but he didn't take off any points. So yeah, it worked out well. So scores are going up. So I'm still in a position to get a good grade out the class. So we'll see how it goes. I have my EM exam next Tuesday. I'm worried about it. I am. But we'll see how it goes. That's why I've been studying EM this week. I still feel like I haven't been studying enough, probably because I was so tired for a while. But I'll show y'all some of what I went over. So, hey, what's going on, Lisa? Good to see you. So yeah, I'm glad it went well. So still in a good position. Still could do really well out the class. I just have to do really well on my final, and we'll see how it goes. I already have an A in my research classes. So in my classical dynamics, I have a A minus or something right now. But I could technically skip that final. I wouldn't mind just taking a B to lift up my other two classes. So we'll see how it goes. Yeah, I'm doing good, doing good. So having fun. Still think my favorite class is my astronomy research class. Because I just enjoy it so much. Uh, which is part of what I'm doing my project for. Part of my project is for that. My professor allowed me to do my actual. I mean, I can't actually fit the entire research project into the class thing because he just wants like 2 pages and like one image, so I got to like cut it down for the class, but it still allows me to utilize the same data and what I'm doing, so that's good. So I'm sure that'll doing well with that so far, and I can't wait. I imagine next year I'll have enough of the research done, like the full research, where I'll be able to, I plan on giving a talk again, so maybe I'll go on MC Toon's channel and present it, and maybe contact that college I spoke at and present it there as well. But more to come on that, on what I'm doing on stars. It's awesome. The topic for the day. So as promised, I'll be talking about some electromagnetism because that's what I'm taking an exam on soon. I was debating on what specifically to discuss because it's all complicated stuff. But I think the speed of light and how we can derive it from basic principles is a good place to start. And I can also talk about my own research there. So what you're looking at here is my graph from Modern Lab that I took the summer of this year. So Modern Lab at UT at least is a lab. I'm sure it's similar to most modern labs in the universities. But basically, you're given a week during the full semester, 2 weeks, to do an experiment on your own. You can pick your own experiment, And being that I know I'm going to get into astronomy, I was anxious to measure the speed of light. And what you're looking at here is a plot of the different sort of the line is the fit line, and all the dots show the different measurements that we did. So basically, what we did was this is the generator of the signal. So this function generator actually generated a signal that went out as a laser. So I spoke in my last debate how they send signals to the moon and that they send specific signals so they know they're getting the signal back. Something like this would be one of those things where this is connected to a laser. It actually looks like a laser in the background, but it's probably not what we were working with. But you connect this device to a laser, and it actually makes the laser send out a laser in certain pulses. Like, of course, we can't see it with our eyes, but the oscilloscope, which we'll get to in a moment, it can pick up when it receives a laser beam, it can pick out the signal, right, and show it. So, for instance, if you look at this oscilloscope in the back, those waves, it can actually pick out the data that's encoded in the signal of the laser that's input by the signal generator. So I'm pretty sure the one that they use to send to the moon is a lot more advanced, but this is basically what they do, right? They encode data into the laser signal. So when they get the laser back, they know they have their particular signal. And of course, the way the thing on the moon is designed is going to send light straight back to you. But light does spread. So I guess it's conceivably possible to pick up some light from somebody else's signal. But the people who send out their signal, they know the signal they're sending and know the frequency and the modulations that are in it. So they get exactly that. So this is a close up of the screen of, like if you look at it, you can see it's in the 500 microsecond range. You can see the peak, the frequency. So all of these things are encoded in the laser light that's going out, and this oscilloscope can pick it up. Now, this would be the laser. So if you see this box right here, that's the actual laser that we were sending out the laser with. And this thing on the right here, this is the receiver, right? So, and I'll scroll through some pictures. So this is basically the all set up in one situation. And this may not be the particular mirror we were using, but this is an example of one of the mirrors that would reflect the light back from the laser. So looking at an image of the setup, here's the mirror here farther down in the hallway. And this is the oscilloscope, the signal generator, the laser right here, and the receiver here. So what we're doing is we're sending the laser down to the end of the hall towards the mirror right here. And then we adjust the mirror so that it sends the laser light back into this receiver. Again, the laser has a code input into it so that we can very clearly see the wavelengths, the frequencies, where the differences that we're receiving it at. So one of the signals are going straight to the oscilloscope, and one of the signals are going through the laser to the receiver and to the oscilloscope. So then what happens is when those two signals put into the oscilloscope there, you see right there, we can match the uh the alignment of the signal directly from the oscilloscope and the signal that's bouncing off the mirrors. And that difference will be because the difference in time it takes for the light to pass down the hall and back compared to straight to the oscilloscope directly. So this is you can see the laser beam right there. Of course, the mirror is not perfect, so some of it bleeds away, but most of it goes back to the receiver. And this is a long view. So this room right here is the lab. So there's other people in that room doing different types of labs. That's actually my lab notebook in my book sack right there on the left. So this a professor wanted us to write all of our notes on hand. We had to turn in this notebook to the TA so it can be graded. So that's where I actually wrote all the notes and everything I was doing and kept good records. And it became a good habit actually. And this is the measuring uh, uh, what do you call it? I forget, tape measure. That's right. This is a tape measure where you measure the different distances, and we did it by several different distances. So this is an example down the hall, the opposite way. You can see the mirror down there. Basically, what we did was we did like what 20, 10, 20 measurements at different distances, So we can go ahead and average out the different ones. And that's why if you look at the first image here, the graph, you can see the different distances that we utilize uh, from 1 to 6 meters and the different times that it took to go those different distances. And you can see the very linear um, way that the time and distance scales. At least it says so the graph with the time and distance of those measurements, that's correct. So we would, for instance, so let's look at this one. So we put the mirror, let's say a meter down the hall. So that means it takes a meter for the signal to go there, a meter for the signal to come back. So that's 2 meters. And it took this many microseconds for the signal to go that distance and back. So we plot that. And then we put the mirror like the more distant you put it, the more difficult it was to get to get the laser to focus right back into that detector. So there was a practical limit to how far we can do it, even though after the thing, the professor, they have all kind of tricks. So after the thing, he told us some different ways we could have did it, but we did it the way we did it and we got some good results, but it was kind of challenging to get in the mirror pointed properly and everything aligned properly. But so this one, for instance, we set it at 6 meters and it took two what microseconds for it to come back, or did I write that wrong? Maybe 10 to the 8 microseconds for the signal to come back. And so basically, if you plot this, the slope is going to be the speed of light because the distance over time, meters over second, is velocity. The character says there all is the rest scattered, if only most of it reaches the sensor. It's scattered much. Like it's very, because it's like just like how if you look in a well, I guess the only way you can really do this is describe it with a laser. But suffice it to say, if you look at the side, you can see the little dot. But if you look at the actual device, I'm pretty sure I took a picture of that because I was really good about taking a lot of pictures. There it is. So if you look at this dot, this red dot, let me see if I can zoom in. So there it is right there. Now, if you look at the red dot, that's the laser. But if you look at this dark spot, that's the sensor. So as you can see, it's still pretty strong, even though a little bit of it bleeds off. I mean, it is a laser, so it's very coherent light. So what we had to do was we had to adjust the mirror so this little dot went into this little bitty receptor right there, right? And the farther away it was, the more difficult it was. So yeah, enough still went. Now, another thing we had to do as well, by the way, if you look at this signal generator, we had to address the strength on that as well. So that's part of it too. So this device, not only does it give the signal, like you could adjust all of these knobs on here. You can give it a sine wave sort of signal. You could give it a square wave sort of signal. When I'm giving it a square wave, if you look on the left, is like a yellow square wave, and you can give it strength, or you can boost the strength and weakness of the laser. So all of that stuff we had to had to play with and adjust so that we can have a strong enough laser going into the thing and the signal enough where we can read it, right? Because if the signal is too tight, it makes it more difficult for the oscilloscope to catch it. All of that stuff we had to adjust on our own and make sure that we can get the data properly, right? So good. So two good questions. So that was that. And in the end, we got the speed of light, 2.9 meters per second. I forget the exact amount. Maybe I should have put the slope value on my graph, but that was like my first experiment that semester, so I could do a lot more with graphs now. But that was that. So and it worked out pretty well. So so that's how I knew the speed of light, because I was able to measure it myself, and I wanted to be able to see that, especially going into astronomy. Now, what we're going to talk about next is uh the the fact that that's mathematically determinable. Let me get this showing, and I'll pull up my notes. I still can't do this by heart. We close this. Here we go. So what we're going to do now is look at the how, because basically what the part of electrodynamics we are right now, because electrodynamics is like the class I'm learning assistant for is like a beginner level of the class I'm actually in. And we start doing electromagnetic waves in 3 dimensions, and we start doing relativity. We start because I didn't know this, but Einstein actually utilized electromagnetism to come to his understanding of relativity. Is actually quite interesting. And the more I learn, the more it shows us how stupid and ignorant these dirt people are, these flat earthers and geocentrics who think they understand electromagnetism, and even some of them saying gravity is the electromagnetism. It's just the depth and the understanding and the reality of what's going on is just so amazing. It just is it just amazing that these people believe that they know what they're talking about. But so Einstein actually recognized that. Well, I mean, all physicists recognize that if we have, for instance, a wire and we have a magnet, there's a flux going through this wire, and if we move this wire back and forth, we move the charges in the wire, and the charges will move according to the force is going to equal QV cross B, and that'll give us a current, an induced current in the wire. Or at the same time, if the wire is still, but we were to move the magnet back and forth, so the magnet is going back and forth, what'll happen this time, it'll give us, let me make sure I use the right equation, it'll give us a voltage from an induced voltage from the electric field. So it'll work off this equation. So when the wire is moving, it works as if the field is coming from the current is coming from the magnetic field. And if you move the magnet, it works as if the field is coming from the electric field. So, and actually I reverse these. It's the electric field for the magnet and the magnetic field for this moving. So let me reverse these. So it's actually like that. So basically what they realized was that these the forces that we understand to be at work depends on the perspective that you're looking from, even though the same thing is happening. Like if you're sitting on this wire, it looks like the magnet is moving because you're with the wire. So then it seems like the magnetic field is causing the current. But if you're sitting on the magnet, it looks like the wire is moving back and forth, and it looks like the electric field is causing the uh, current. And people were like, well, which one is it? How can it be both? And Einstein basically utilized things like this, like real experimental occurrences like this, where two different perspectives gives you the same thing from two different equations to uh, to eventually get to the realization of relativity. And that's what he first actually proved it at with electrodynamics. So our understanding of electrodynamics, such that allows us to even be talking right now, because the power plant is working on these principles. To and the high voltage wires are working on these principles, and the capacitors in your computers. All of these things are working by these principles and equations. So we know they work, and we know that they're not what the flat earthers say they are, because we have electricity. And then Einstein was like, okay, all of these things work, but they work differently on from different perspectives. And then he eventually got the solution, and now we have special relativity. So the question is, how do we get the speed of light from this? Because light is going to be an electromagnetic wave. That's why we call it EM. It's going to have an electric component that's going perpendicular to a magnetic component. So both of these things are at play in light. So this is why it becomes so relevant when you're dealing with light or electromagnetic radiation, period. Depending on who you talk to, light is going to be, uh, you know, some people say that radio waves are not light, but depending on how you want to define it, is all light. It's just different electromagnetic radiation, and all of these things work on this principle, right? They all work on the principles that we're about to discuss right now, that I'm about to show you mathematically. So what I'm going to do is I'm going to draw and let me actually change the orientation of this thing. Let me make my electric field, I always make my electric field green. Actually, let me just, yeah, let me turn this whole thing green. And what I'll do is, so the electric field is going up and down. We'll say that the magnetic field is coming out this way. So this is the magnetic field. So what I'm going to do is I'm going to put an axis on this, and I'll show you all how we can derive the speed of light from first principles that, again, we utilize to give ourselves electricity and power plants and capacitors in our computers and all of these things that work, that show that the idiots who say all this stuff is wrong and gravity is electricity or whatever is just nonsense. So this is our z-axis. I derived it slightly differently from, I mean, I derived it the same way my professor did, but I utilized the axes a bit differently so it can make a bit more sense to me. And the way it works is this electromagnetic wave is changing as it goes along. So, and trust me on this, and then I'll show you mathematically momentarily. But we can say that this electromagnetic, the strength of this field here is different from the strength there. So it changes as a function of moving along the y-axis. So we can say that the electromagnetic field here is EZ, and the electromagnetic field here is EZ plus a change in EZ. So there's a little bit of a change in time as it moves along. And let's make sure I didn't miss any question. Okay, good. And we can say the same thing with the magnetic field. We can say that the magnetic field, we can call this Bx because it's on the x-axis right there. And the magnetic field here will change over time because that's what allows us to get electromagnetic radiation is basically a self-creating wave in which the electromagnetic wave changes. And the changing electromagnetic radiation produces a magnetic radiation and vice versa. So, and we can see this with these two equations here. So the first one is the recognition that we can get if we do a closed or line integral of an electromagnetic field over a closed surface is going to equal the negative flux over time. So that's going to be our first equation. And this equation is the magnetic line integral over a closed surface. And this is going to equal mu naught epsilon naught, the change in electromagnetic flux. So things that show this to be the case is if you have, for instance, radio station. So if you have a radio station, for instance, what the radio station does is there is a antenna, and an antenna has an electrical current or signal going through here that they change. And when they change this electromagnetic signal, it creates a magnetic fields around it that change because the electric field that made it is changing. And what happens is this in turn creates another electric field, which creates a magnetic field. And this is how we create electromagnetic radiation that comes, for instance, from your cell phone. If your cell phone has an antenna that has these changing currents, which creates the magnetic field, electric field that propagates through space. It hits the antenna at the station or wherever, and it causes a resonating electromagnetic field, and then that can in turn be translated into what the computer can understand, and then you hear a voice on the other end. So we intimately know that this is the case. That if you have a changing magnetic field, it creates an electric field. If you have a changing electric field, it creates a magnetic field, right? And so what we're going to do is we're going to use this concept and we're going to integrate over the electric field and the magnetic field. And we're going to have to take some derivatives. And out of this, we'll see why the speed of light is what it is why the speed of light happens to be what it is and the limit of how fast things can go in the universe. So the first thing I'm going to do is I'll start with the electric one with the equation 1. And what I'm going to do is, and if there's any questions, let me know. What I'm going to do is I'm going to take the difference, you can say, of the area between these waves here. So my line integral is going to be over this area between these two electromagnetic waves. And if we look at this, we can say that it's difficult to draw this because technically these waves, magnetic radiation is a plane wave. So if I was to draw it more accurately, it'd be more like a bunch of electromagnetic waves like this in like a wall of these things, and there's a bunch of walls moving forward. So this drawing is not quite accurate because if I drew it accurately, then you won't be able to discern anything. Just be a big wall of blue and red mixed together. You just won't be able to see anything. Just understand that there's a plane wave moving along, and basically the magnetic field is interacting through here, and that's giving me my direction. And I'm going to take an integral around that closed surface to figure out what the electric field, how that relates to the magnetic flux that's going through that same area, that's causing the interaction where they create each other, right? So the magnetic flux that changes creates the electric field, and the electric flux that changes creates the magnetic field. So we're going to calculate that. And again, let me know if you have any questions about anything or something is unclear. So when I do this integral, again, it's a line integral. So I have to do 4 integrals around the uh, area that I'm dealing with. This is my area here. And if we look at this, the electric field is in the z direction. So there is no electric field uh, here because the electric field is in the z direction and that's in the y direction. And there's no electric field there. So all we have to do is do the electric fields at this point. And we can say that here, the electric field, we can say is going up. And we can say the direction I'm doing my integral is going in the same direction. And we can say here the electric field is going down in that direction. But we could basically my loop is going here, but this is still pointing up there in the opposite direction. So what we can do is basically take that into account in our negative signs. So what I'm going to do is I'm going to skip the 0 ones. And if I call this, let's say, A, and if I call this A, let's say, and maybe I should probably move this over the whole wave. And we're going to say, I'm going to take an integral from 0 to A of the EZ plus DEZ ds. And I'm also going to take the integral of 0 to A EZ ds, and that's a dot product. All right. So basically, I'm taking the integral here because there's an electric field there, taking the integral here over the electric field there. And I'm going to call this point here A, and I'm going to call the origin 0. So therefore, I'm taking an integral from 0 to A in both parts. And this will actually come with the next one. So this is A along the y-axis. This is A along the z-axis. I'm going from 0 to A on the z and 0 to A on the z. And the direction here is going to give me the value of my sines. So basically the AZ one, if we look at this, again, this wave is going up here. My arrow is going up. So the cosine there is going to be 0. This becomes 0 to A, EZ plus DZ, cosine 0. And this is going to be plus integral 0 to A, EZ, and cosine of 180. ds, because here the wave is going up here, but my arrow is going down, so I'm going in the opposite direction, so I have to take a negative of that. And this ds is simply the integral over the length of that segment. So this is going to end up being ez plus dz. Cosine of 0 is 1, and this is going to be I guess I should say z to the 0a, and this is going to be minus, since cosine of 180 is negative 1, ez z 0a, right? So when I complete this, I'll end up with d e z a, because this positive one and this negative one is going to cancel out, and now I'm going to add the other side of the equation, which is this. That equals negative d, the magnetic flux over dt, right? Now, the magnetic flux is going to be basically the area and the amount of magnetic field that goes to that area. So I end up with negative d over dt, the magnetic field in the area. And the area is going to be this area here, basically the area that the magnetic field is going through. And remember that this is like two plane waves, so there's like walls going on there. And we can see that the magnetic field is going in the x direction, so that's why I consider this the direction of flux, and how it's going to end up being 90 degrees, because they're always 90 degrees to each other. So this area is going to be negative d over dt, b, and it's still going to be a, which is the height of this thing, and then dy, because I'm moving along the y-axis on the other version. So I have an area here that's a tall, and dy long, depending on how far I go along, right? So now we have almost the first equation. Now what I'm going to do is I'm going to take these two ends here. These are the ultimate ends of the equation. These two a's cancel out. And if I divide by dy, what I get is dez over dy equals negative db over dt. And this is bx, since the magnetic field is going in the x direction. And looks like I have that correct. So let me know if anybody have any questions about what I did so far. And I'll see if there's any questions about anything while I start setting up the next one, which would be utilizing equation 2. Looks like everybody's good at this point. So, and how long do I have? Yeah, I have enough time. So, utilizing a similar approach here to get the other equation, and this is going to be bx this time, ev, because the magnetic field is along the x-axis. And it's going to be the same type of integral. Basically, I have an electric field that's basically going through this magnetic field here. So we can see the electric field is here. And I'm going to similarly draw my area that I'm integrating over, which will give me the directions of my sine or cosine angle when I do my integrals. And basically it goes along the same direction as if the magnetic field is coming out the page, because EZ is going upward. That gives me the counterclockwise direction of my arrows. And we'll look at that integral. So this is going to be the same thing. I'll end up with an integral for the bx plus dbx. and the integral of the bx because there's no magnetic field along the y-axis. So I'll end up with integral from 0 to a of Ez plus d Ez ds plus integral from 0 to a of Ez dot ds, right? And the same thing will happen here. So if I look at my uh, dx part, we have 0 degrees for that one. We have 180 for the easy one. So I end up with this. This is still the integral of this plus we have that. So similar thing will happen when I cancel these out. I'll end up with Ez plus d Ez minus Ez a, and that's going to equal a d Ez, and it's going to equal the other side of the first equation or the second equation, which is mu naught epsilon naught, and the flux, the electric flux, since it's the electric flux that's causing this change over dt. Right? Now, something is going to happen. This is going to be uh, a d Ez. Oh, this is magnetic flux, I meant to say. And this is going to be mu naught epsilon naught and d over dt, the area and the magnetic field that's causing the disturbance. And let me make sure I didn't mix up any of my. Sometimes I write B when I mean to write E. Yeah, all of these should be B's. So I started writing B by mistake. Hold up here. B and good. So mixing up my notation a little bit. Bear with me. Let me correct these. All of these should be BX's. Boom. Right. And this is my E. And it's going to be the similar thing. It's going to be mu naught, except it has the extra constant in the front. We have mu naught epsilon naught d over dt. E, and the area is going to be A and D Y still, because it's moving along the Y direction. We'll do the same thing. The A's here cancel. I can divide by dy. You will end up with d bx over dy equals negative mu naught epsilon naught d over dt. And that's going to be Ez, right? So that's what we have for our next equation. So if I was to put these together, we have this and that right there. So this is what we get from integrating. And seeing how the electric field, a changing electric field makes a changing magnetic field along a certain direction, and a change in magnetic field over time makes a change in electric field along a certain direction. And again, we're getting to why these things, because they're both changing along the same direction, they're both changing along this direction here. So we're getting eventually to why these interacting, changing fields, electric and magnetic fields, go at the speed that they go at, and we'll see how that leads us to that. So the next thing we need to do is we need to start combining these things because these are electromagnetic radiation. So what we're going to do is we're going to take the third equation and we're going to take a derivative of that to make a second derivative. So I'm going to take a second derivative of this equation here. So this is going to end up being d squared over dy squared ez, and that equals d over dy of negative dbx over dt. And we're going to do a little bit of a simplification here. So I can take and swap the position of these two derivatives here. And now what I have is from equation 4, I actually have something that equation 4 equals. I'm going to input that for equation 4. And it looks like I left off my negative. Well, I'll leave a negative off. Let me have swapped my I think it was my directions. Let's see. Yeah, derivatives are fun. I actually like derivatives in integrals. I know most people don't. Yeah, that's what it was. So this one was 180, and this one was 0. And I end up getting a negative here because the direction is when the magnetic field here is going downward and the magnetic field is coming up. So you have a 180 there, and there's going to be 0 on the other one. So this one, the long one, had the 180 that popped up my negative. So now I have a second negative here, and I take that derivative, which is going to be here. So I'm going to plug that in. It's going to be negative d over dt. I'm just going to go ahead and copy this here. So all I'm doing is just plugging in what I solved for earlier. And when I simplify this, I end up getting, let me make sure I'm looking at the right one. Good. End up getting d squared ez over dy squared, and that equals mu naught epsilon naught d squared ez over dt squared. And what this actually is a wave equation. This is a wave equation because we have a second derivative of something over space equals a second derivative of something over time up to a constant. So this is actually a classic wave equation, which is showing us what we're getting at, the fact that we're looking at electromagnetic waves, right? And I call this equation 6. And then we have to do a similar thing for the 4 equation. So now I'm going to do a second derivative of the equation 4, right? And we'll see how that works. We're going to be d over dy of dbx over dy. So that's going to equal, let me make sure I'm not doing a double of the same. Nope, okay, we're good. And this is going to be negative mu naught epsilon naught d over dy of d over dt ez. The same thing, I could move this thing on the right side around a little bit. Mu naught epsilon naught d over dt. We have dez over dy. And now I can input what I had for that. I had this for, what was it? Right here, dz over dy equals that. So now I'm going to plug this in for dez over dy. So we have that equals negative mu naught epsilon naught d over dt. And that's going to be negative dbx over dt. So I'm just plugging that in. So then what I end up with is another wave equation. I have d squared dx over dy squared equals negative, actually the two negative cancel, positive mu naught epsilon naught d squared over dt squared dx. And I have a second wave equation. And I have two different wave equations, one in terms of the electric field, one in terms of the magnetic field. I'll call this equation 5. Let me check and make sure I didn't make a mistake anywhere. It's good. All right, that looks good. Now, this is the default wave equation. Like if you have just a general wave equation, it looks like basically a some kind of constant. Usually we determine it to be squared, d squared over dx squared, some position, times the wave. And it equals d squared over dt squared times the wave, times some wave. Or if I was to put it in 3 dimensions, it would be partial derivative squared of some wave dt squared 1 over v squared, bringing that to the other side. And then we have partial derivative of a wave x squared plus partial derivative of the wave y squared plus partial derivative of the wave z squared. That's the basic wave equation. And this v, the reason why we call it v, because it's the velocity of the wave. This ends up giving us the velocity of the wave that we're dealing with, is the coefficient of that. Now, if you look at the equations we have, right, we actually have something in front of both of our equations. We have the same thing in front both of our equations in terms of uh, the velocity term. And we can see that if it's in front of the time term, it's inverted, right? So whatever I have in front of time term is the inverse of velocity. It equals the same thing. So I can say 1 over v squared equals whatever that thing is, which is mu naught epsilon naught. So then we have v squared equals 1 over mu naught epsilon naught. So then we have velocity of whatever wave we're dealing with is going to be square root of 1 over mu naught of epsilon naught. Now, these two constants are very important constants. Doing math on computers look really handy, Catherine says. Always got so much pain doing all the work at university. Yeah, it can be tedious. I actually think it's fun, though. I actually like it. Matter of fact, one of the experiments we did, and maybe I'll talk about it in detail one week. I was validating relativity, and what we did was we took some very high energy particles, and we so basically you have, I mean, it's not enough to hurt you, but it is these radioactive materials, but it's stuff like carbon that emits stuff that it could hit an electron and make some changes to it, but it's not going to like hurt us physically. It was able to handle it. So we put this material into this crystalline substance, and the radiation would knock electrons off of the crystals. And then we had a detector that was able to detect the electrons coming out, and it was still high enough that it was knocking it off at relativistic speeds. It was like basically gamma radiation, even of a frequency that didn't really hurt us. And so what we were able to do was get the scattering effects, and we was able to measure the relativistic effects in the speed that the electron was going compared to its mass. And there was many ways to do that equation, but I actually ended up having to do it in a way that I could actually calculate by hand because I just wasn't good at programming. I'm still not so good at programming, but I'm better at now. But it was a headache doing that equation, but it was actually still fun. Maybe I'll do a video on that one day. Where and my understandably enough, my result wasn't exactly what the professionals got because my measurement like I noticed that the measurements of my speeds and all were not quite, it was a little bit off, but the scientists that I was studying, the paper I was studying, they had like a very much more advanced device. Like, we were just in that, you saw the little room. I showed you the dorm, my images, it's just a little machine up in there. It's a good machine, but it's not like the top of the line ability to detect the speeds of these subatomic particles. So, but it was enough to get within, I don't know, so many percents, and it was still fun to do. But the bulk of it, I did it by hand. Now, if you look at these uh, constants, this constant here is called the permeability of free space. And basically what it is the like electric fields, like space has a similar to like an analogy I would liken it to, like when if you have your hand in water and you move your hand through the pool, there's a bit of a there's a resistance to your hand moving. There's a limit to how fast you can move your hand. Given how strong you are, the water is resisting you. And we also know, like from LIGO, that space can be rippled like a sheet. You could wave it if you have a strong enough gravitational force. It's like when these black holes and neutron stars collide, they shake space so much that we could actually perceive the ripple. That's what LIGO does. So, so space in a sense has a substance, how I think about it. And the electromagnetic fields, there's a limit to its ability to pass through space. There's some kind of, I guess you could say, resistance. It's probably a poor way to explain it. That's how I think about it. And the value of this is 4 pi times 10 to the negative 7 henries per meters. So Henry is a unit of inductance. It's dealing with inductance. And epsilon naught is similar, but with magnetic fields. So basically, it's called the permittivity of free space. So the permittivity of free space is similar, but with magnetic fields. Basically, in a vacuum, the magnetic field strength proportional to its flux. Like if you have a certain strength of field going through a certain area, space itself puts a limit on how strong that will read given the strength and the flux. Similar to, again, your hand moving through water, there's a sort of limit, but we know that space has a girth to it, which again, going back to black holes when they collide, we know that space has a girth to it that ripples. And the limit on this that we measured is 8.854 times 10 to the negative 12 farads per meter. And farads has to do with capacitance. With capacitance. So all of these things, again, capacitors are in our computers. Uh, uh, Electric fields, they go there. You uh, we can get what voltage is V equals to IR, and we can get induced currents with electric fields. All of these things relate. Like the technology that we have would not work if our understanding of these constants and the way they interact were not accurate. Apart from what the idiots tell you over the machines that utilize the stuff that they say is wrong. It's like they're calling up on the computer to tell us that all the technology and science behind building the computer is wrong. Yes, as well. Okay, so but if you actually plug this in your computer or your calculator, whatever, 1 over 4 pi times 10 to the negative 7 henries per meters and 8.854, and this is rounded off, by the way. Like there's a lot more units, but I just stopped it there. E to the negative 12. Oh, write this better. Farads per meter. So you can guess what you get if you put that in your calculator. You get. Let me get the exact value I got. I got 299,795,637.7 meters per second, which is the speed of light. Right? So this is why the velocity of electromagnetic radiation is what it is. Both the electromagnetic part and the space part of the wave equations together are limited by these two uh, constants of nature directly. And when you solve the wave equations, you get that the velocity is actually the inverse of those constants squared. And then when you solve for that, you get V is the inverse of those constants, the square root of that, and it outputs the speed of light. So the first half of this thing, I talked about how I measured the speed of light, and I got this. I can get the exact amount for you, but mine was off a little bit. It was like 2.92 or something like that. But it's a pretty crude experiment, close enough. 2.9. It was like 2.92, 2.94. And then when we do a calculation, you get basically 2.9 or 3 times 10 to the 8 meters per second squared. So measurements, and of course, if you look up people who do this professionally, I mean, they get really close to the exact amount, when they use like because I, I believe I'll just show my images again. I don't know if that's still sharing. Just like it stopped. Put up here. Let me share that again. If it's still, looks like I closed it. Hold up. There we go. So is it showing? There we go. So let me share again. Boom. So looking at this, not the most high-tech equipment. We got the job done. We were measuring by hand with a tape ruler, but we were being pretty. Oh, is it showing? Oh, it's not showing. Sorry. We were being pretty fastidious about it. But still, it's not the most high-tech equipment, but it got us pretty close. In our error margin, we did calculations for the error in our measurement of the distance. We did calculations for the error in our signal ratio, and our value still was within the official value, given our error margin. So we still were, officially within but we had a pretty large error margin relative to like if somebody did it at like with very high tech equipment. Similar to what I was saying, how when I confirmed relativity, the values I got was still off from the paper I read. I mean, it was off enough where my value was not so precise, but I was able to confirm relativity is real. So that's all I really had today, y'all. So, and it's about time, but if I have any questions, I can still answer some before I go. Lisa said, did your professor require an error analysis in your measurements? Yes. If you do not do an error analysis, you will lose a lot of points. Yeah, in science, you always have to account for error because no measurement is going to be perfect. Looking at the tape measure we had, there's a certain error in the tape measure. The people who built it, they had, so maybe the machine had an issue. Something was not going to be perfect about that device, that measuring device. And maybe the way I hold the ruler, maybe I hold it differently. And I think we tried to alternate things a bit. So I don't actually know because a few of us, like I had our lab partner, and I did some things better, and he did some things better. So usually we did the thing that we did better. I actually ended up being pretty good about uh, adjusting the mirror and stuff like that. So I mostly did that, and I think he was pretty good about measuring a ruler. So he mostly did that, but still he did it by hand, looking at it with his eyes. Nothing is perfect. But what you can do is when we look at the ruler and we can say, oh, we measured it. Like we basically what you do is you look at, let's say, how much uh, uh, accuracy a ruler has. So let me go back to the spreadsheet, to the handwriting here. So if you're looking at your ruler, let's say this is 1 meter, and let's say your ruler has a precision up to, let's say, 0.5 meters, right? So that means that if I measure something here, it's going to have it could be plus or minus 0.5 accuracy, I guess you can say. But of course, it is a bit better than that because there's a whole bunch of little lines. But basically, when we get in this realm, we sort of consider either side to be our error. You know, this thing could be a little bit off this way, it could be a little bit off that way. We don't really know. So it ended up being, it was something like a few millimeters off, but still, we was able to look at our ruler and see where our things were falling at, and we was able to give an error margin for that. And then we were able to, for instance, that's why we took multiple measurements. We was able to see the difference between the measurements. So once you put all of these measurements into a program, it can actually calculate for you. Okay, you measured the same thing at different distances, but we can see that your measurement here and your measurement there, it can look at the differences and it can output what the error margin was for those things. So all of that stuff we have to take into account, or you will lose a whole lot of points. I submit it via latex? I did not then. I was not that high tech yet. But now, since I'm in my upper level classes, is a requirement. Like for my astronomy class. Matter of fact, for the papers I'm writing for my rotation project that I'm going to present to y'all probably next year, I have to write everything in latex. Like we cannot do it. Like if you don't do it in latex, then you just get like a zero. So rule, so basically from now on, that's what I'm gonna have to write it in latex. But at the time I did this, I didn't. I just wrote it in like a regular word processor program. I actually started writing in latex before, but I mean, they have a lot of things that make it a lot easier now. Like it almost does it for you. When I first started writing in latex, it was a lot more manual. I was like, hell with this. I didn't have to do it, so I didn't worry about it. But now I have to, so I'm making it work. So yeah, so it's not that bad. Oh yeah, yeah. So oh yeah, when I copy one down, yeah, this thing is pretty nifty. I love it when they let me. Some of our classes they let us take exams on it, and I could just copy paste some things and save a lot of time. I bet it's pretty nifty. So I'm pretty sure I wouldn't. My grades put it like this would be a lot worse if I didn't have this thing because it saves so much time. Uh, when I'm doing homework, I could do it here and just spit out a PDF. I can copy stuff very quickly, duplicate things, so it saves a whole lot of time. So yeah, I knew, and I've seen people like there are people who are in my class who don't have. They just do everything on paper, and it's terrible. Like I remember seeing this guy. He used to come to my study group sometimes. Sometimes I host study groups, and he was like studying for an exam, and he was like he had all these notebooks, and he was flipping through all of them trying to. I was like, I don't want anything to do with it. No, yeah, very painful. Glad you like the Catherine. Catherine says very very fascinating. As a computers, I think I got every question. Oh, Lisa said, why the second derivative at this point? I can't say I remember the details of why the wave equation has a second derivative. Uh, and that's the only class I got a C in actually. This was the waves class. I probably should have retook it and just got a higher grade. But it's just characteristic of a wave equation. Maybe what I can do one week, I can do a talk on the wave equation and why that's the case. But I gotta let you know that wave equations is going to be a second derivative equation, and that's the nature of it. It could be because, like, just thinking about derivatives, if you have, let's say, a curve, uh, the first derivative will give you the max and min. So if this is a sine curve, for instance, uh, let's say just say my psi, right? If I take d psi over dt, if this was t and this is psi, and this is my graph of psi, the derivative will give me the max or min if I set it equal to 0. If I set this equal to 0, this is actually the slope. And the slope will be 0 here at a max and 0 at a min, right? So that's the way that works. And if I take a second derivative, so if I take uh, d squared psi over dt squared, this will let me know if it is a max or a min. Like this here will just let me know if it is a max or a min, if it's 0 at that point. But this second derivative will let me know, is my slope going up? What's the change in my slope? Or is my slope going down? This second derivative will tell me, so this will tell me max or min. And this will tell me, is it is it a max or is it a min, right? So I'm sure that has something to do with it. Simply the very nature of a second derivative, it tells you the change in slope. And when you're looking at a wave, that's literally what's going on. Basically, the change in this thing is building or creating a magnetic field, and the change in this thing is creating an electric field, as I showed in these equations here. The changes are equal to each other, but with reverse. And the fact that these equations work at a right angle shows that they're orthogonal to each other. This is where the uh, uh, well, actually, I didn't actually show that in this one. Well, I thought I did, but I guess what was a good one? Well, technically, I guess just the velocity. Like if you have a wave, the electromagnetic field will be at a right angle to the magnetic field. That's just always the way it is. And we just count polarization. So in that sense, it probably has something to do with that, but I can't remember exactly. I should remember it, but yeah, like I said, that wasn't my favorite. That wasn't my best class. And, and I think that's all the questions. Welcome. So glad you all enjoyed. Hopefully it was informative. Some math heavy stuff, but now you're able to see how what's the word, experimentally we can get the speed of light by simply measuring it like I did. And if we just do the math, take the integrals, take the derivatives, we end up outputting the speed of light from the values of the core concepts that we use to build our computers and power plants and power lines and all the things that we utilize that show that our understanding of electromagnetism and gravity and all that stuff is accurate. Also, we wouldn't be talking right now on this computer. It's awesome. I don't have a planned topic for the next week at this point, but it'll probably be either EM or quantum because those are the ones I'm going to focus on for my finals. Um, Maybe some research stuff as well. I'll see. But if anybody have any suggestions for what to do on a future vid, just let me pop my YouTube channel in there. And what you can do is you should be able to see, and actually I could just go straight to the community thing. Just make a comment here on community or on this video. Make a comment somewhere. Let me know. And I can make a video about that. It's awesome. Good seeing you, Catherine. Good seeing you, Lisa. I thought I saw somebody new as well. Good seeing you, Zeus. Good seeing anybody else who watched but didn't drop a line. Feel free to comment, ask any questions later. If I made any mistakes, let me know. I'll be looking for any corrections. And I'll see y'all same time next week.